remediation. It is time to explore plastics and how it is an emerging contaminant on this era of urbanization. So, to disseminate us with the topic, it is my pleasure to introduce Dr. Professor Regina Nogueira, ma'am. Professor Dr. Regina, ma'am, is a professor at Institute of Sanitary Engineering and Waste Management at Leibniz University, Hanover, Germany. She pursued her master's and PhD from University of Minho, Portugal. She is specialized in chemical and biological engineering. She's also worked as teaching assistant and assistant professor at University of Minho, Portugal. In 2012, she joined Leibniz University as a full-time professor. So I invite her to enlighten us about plastic monitoring and analysis in water systems.
Thank you very much for a very kind introduction. I would like to address my sincere compliments to Professor Kirmala for the invitation today to be here together with you and to give a presentation. It is also a pleasure to be here in IIT Indoor. I feel that now IIT Indoor is my second university. We started working some years ago. Now we are working in the common project and we plan many more activities for our future. It's a pleasure for me to be here speaking for young people, young scientists. It's always motivated and your questions are very welcome at the end of the presentation. Then today, my topic, you are having a hands-on workshop on characterization and quantification of emerging contaminants. And for today, my emerging contaminants are plastics. More precisely, microplastics or macroplastics. And how can we monitor them in water systems? Just a very brief introduction. This is my university. This is the building, the administration building of my university in Hanover. It is the Leibniz University of Hanover. We have around 29,000 students and 84 degree programs. We have courses in natural sciences, engineering, humanities, social science, as well as law and economics. And the city of Hanover is the capital city of Lower Saxony, and our symbol is the horse. It means the symbol of Lower Saxony is the horse, and we are very proud of having this horse that is in front of the building of our university. Then, here is a short roadmap. I will try not to be very long because I know we are close to having lunch. Then I will be very focused and precise so that we have time at the end for questions. It means I will make a short introduction about microplastics. I will mention the methods that we can use to detect them, and several of these methods you had the opportunity in this hands-on course to learn. Then I will present three case studies where we use these methods for the detection of microplastics and macroplastics. It means these three examples that I will give you, they are like the hands-on. How can we use all the theory that we learn in three practical cases? Then, what are microplastics? Very short definition are tiny fragments of plastics that have a size that is below 5 millimeters. It means all fragments that are smaller than 5 millimeters, they are called microplastics. They have different shapes and sizes. They can be found as pits, fibers, irregular particles. And it's important, they have two main sources. We can have primary microplastics and secondary microplastics. Why do we care about such tiny particles? They are so tiny we could ignore them, but we cannot ignore. And there are three main reasons. One reason is that they bioaccumulate in marine organisms. The second reason is that plastics, to have their functionality, they have lots of additives. And these molecules have many times undesirable properties for our health. And the fourth issue is that these plastics, they can absorb from the environment several compounds that might be toxic for organisms and for human beings. Okay, then very shortly, what is the main difference between the so-called primary microplastics and secondary microplastics? Okay, the primary, as the word says, are plastics that are directly released into the environment. And some examples are the scrubbing agents and cosmetics. Another source are the erosion of tires and abrasion of synthetic textiles during washing. It means these microplastics, they are directly released into the environment. These ones. And the secondary microplastics, they originate from the degradation of larger plastics, degradation by the sunlight, photodegradation, degradation by other weathering processes. Okay, we have these two categories. And now, which are our main sources of microplastics? What is the world consumption? And are these plastics intentionally released in the environment or not? And here you have our main sources of plastics into the environment. We have the plastic pellets, synthetic textiles. We never imagined that each time we wash our clothes, we are producing tons of microplastic, microfibers. The tires, road markings, marine coatings, and personal care products. And the biggest amount is coming from the plastic pellets. And the lowest amount from the personal care products. And both the plastic pellets and the personal care products, maybe we can find a solution not to introduce them into the environment. And now, let's see a life cycle assessment of a plastic product. What happens from the production to the deposition? And we have here the plastic cycle. You have these two darker dots. We have the product life cycle, and then these two arrows we can distinguish between microplastic generation and microplastic primary generation and secondary generation. Okay? If we start here we have the production of the plastic itself. Then from this plastic we can manufacture several products that then they come in use. And here, when we start using these items, we have, as you see here, the generation of different primary microplastics. Afterwards, these items are disposed. If we dispose all our plastics correctly, what would happen? We would recycle them. But we know that a big portion of our plastics, they are not recycled. They just escape this recycling and they end up in the environment. And due to photodegradation and due to weathering processes, we have the generation of the secondary microplastics that at the end, they end up in the ocean and they accumulate there more and more. The message is we need to reduce the input of these primary microplastics in the environment, and we need to improve our recycling so that part of the plastics do not escape anymore this recycling trend. Okay. Then you can tell me, okay, we have microplastics in the wastewater, but when we have wastewater treatment plants, what are the wastewater treatment plants doing? And I can tell you, they do very well indeed. If you consider domestic wastewater treatment plant, and when we measure it, the amount of microplastics in the effluent and in the effluent, it means in the water, we observe that more than 90% of the microplastics, they are removed. Then we say, oh, our wastewater treatment plant works very well. Yes, they are removed, but they don't disappear. They end up into the sludge. As you know, a wastewater treatment plant is a living being. A wastewater treatment plant uses biological processes, uses bacteria. And what happens to the microplastics? They are caught in this biological flux. It means they just go out of the water and enter the sludge. It means all these plastics that are eliminated from the water, at the end, they accumulate in the sludge. And what happens with sludge? We can have different possibilities for the sludge. You know, many times sludge, they contain a lot of nutrients. And we are spreading sludge in the land to substitute the chemical fertilizers. Why not? But then what happens? We bring our sludge from the wastewater treatment plant. It's a very good fertilizer. We have been using sludge as a fertilizer for ages. This is not new. The plants like it, but we are spreading all these microplastics into the soil. When it rains, the microplastics, they are washed out, they enter the soil, and they are going to contaminate our groundwater. And since in many places of the world, groundwater is used to produce drinking water, at the end, we will have the plastics in our glass of water. Then we try to quantify the amount of microplastics directly in the sludge. And if you look to this picture, the sludge does not look very nice. And also this brown mass is a matrix that has a huge amount of organic carbon. To find the microplastics here is a detective work because it's extremely difficult. It means in this sludge, on one side, we have a very high amount of microplastic, but in another side, we have even more organic matter that makes very difficult to find the microplastics. It means when I started working this problematic some years ago, we did not have a method to quantify microplastics in the sludge. Then we developed a method ourselves. It means we developed a method to be able to quantify microplastics in such kind of metrics, which is very complicated. Then I would like to ask you a question. Here we have several pictures that they were obtained with Raman spectroscopy. And some of them are plastic particles, others not. Guess for yourself which of those are plastics. Look at them, 5 seconds. Don't think so much. Write down, don't tell. Write down in a paper which ones you think they are microplastics. And then let's see if you were able to guess. Fast, 5 seconds. Which ones are the microplastics? Ready?
Okay.
Okay. Then I will show you the result. The microplastics are the ones that have the red cross. Then I ask you, is it easy to identify? Not at all. It means for the identification of microplastics, we need sophisticated methods. Only looking at them, it can be a plastic, but it can be another thing. of the methods that you can use to find the microplastics, to detect, quantify. Look, this process is time consuming. Who wants to work with microplastics needs to have a lot of patience. It's time consuming. And then it has multiple steps. It means if you have a very complex matrix, in the beginning, you have to remove all the organic matter. Otherwise, you don't see your plastics. And for that, we can use different methods. We can use an oxidation of the organic matter. We can use a density separation. We can a membrane separation. It means the first step is only to separate, clean, and concentrate your microplastics. This is, without this step, maybe you don't find anything. When you did this step, then you go for the chemical identification. What type of plastic? Is a polyethylene? Is a polypropylene? Is a polystyrol? You want to know what type. And for that, you have three possibilities. Or you do Raman spectroscopy, or infrared spectroscopy, or pyrolysis gas chromatography mass spectroscopy. Only with these methods you can determine the type of polymer. And then it can be also that you want just to quantify the number of particle plastics that you have in your sample. And for that you can use microscopy, light or fluorescence microscopy. It means when you want to identify the type of polymer, you have to go to these methods. If you want to quantify, you can go for light or fluorescence microscopy. Okay, this is a little bit the basics, and now in the three case studies, I will just mention the methods that were used. But never forget that the first step is the cleaning. If you need, but usually our samples are not very clean, it means we have to clean them in order to detect the microplastics. Okay, and then since we wanted to detect the microplastics in this sludge, we had to develop a method, and we call the method heat and bleach. Why? We use bleaching agents to degrade the organic matter, and since this degradation happens faster at higher temperature, we call our method heat and bleach. Okay? And what did we do? This is here very briefly. Here you can see again the three steps that we used. We had our sludge. We contact the sludge with hydrogen peroxide. This is an oxidation agent that will degrade the organic matter. We rise the temperature to 70 degrees because we don't want to wait 1 week for the process. Afterwards, we separate the plastics using density separation, and we collect the plastics in one filter. Okay. Then we have our sample to be analyzed. The plastics are already in the filter. If they are in the filter, then in this case, we went for Raman spectroscopy to identify the type of polymer. Okay? This density separation, here is only a photo of the lab procedure. You have here the sludge, and you see after the sludge is this dark brown. After digestion with hydrogen peroxide, the color is much lighter because the organic matter was digested. Then I have to separate the plastics, and afterwards I have to put the plastics on top of the filter, and I need a filtration unit. What is this density separation? You know, the different plastics, they have different densities. Okay? And I can, for example, separate the very heavy plastics from the not so heavy plastics using a solution that has a defined density. Okay? In this case, we use the sodium nitrate, sodium thiosulfate solution, that the density, the theoretical density, allows us to separate between the very heavy plastics from the lighter plastics. Then we observed, because we wanted to control did we clean well the plastics, and we made a microscopy. As you see here, we can very well find our plastics. It means our cleaning process was good. And also with the microscopy, we could count how many plastic particles we have, and we could measure the diameter or the equivalent length of each plastic. And at the end, our quantification told us, for example, this is one of the results, that we have these particles per 100 milliliters of sludge. I can also quantify the particles, number of particles per gram of dry weight of the sludge. And in the literature, these are the typical, how can I say, representation of the results that you find. You find the amount per volume or per weight, and you find the type of polymer. Okay? It means what was important here is the cleaning. Afterwards, the quantification is straightforward. If you have a complex matrix, you have to find a way to clean your sample. Here an example of the Raman spectroscopy. Here we have the image, and from this image we obtain a spectrum. And then how do we know the type of polymer? Because we compare the spectrum that we obtain from our particle with a reference spectrum from a database. And by comparison of spectra, I can identify the kind of polymer. Okay, and then based on our results, we made some calculations. We calculate how many tons of microplastics we are putting per hectare and per year in our province. You see here, this is the Lower Saxony province. The Hanover is here in the middle, and this province has a lot of agriculture. It means they put a lot of sludge into the fields. And based on the amount of sludge that goes into the fields, and we knew the amount of microplastic in the sludge, we calculated that in our province, we put 1.6 tons per hectare and per year in our fields. This is a lot. And what we really don't know very well is that when it rains, the particles go to the groundwater. And we don't have studies yet of how many particles we have in our groundwater. In Lower Saxony, we changed our legislation, and now we are no more allowed to put the sludge into the fields. It means all our sludge will be incinerated for energy generation. On one side, we say, okay, we don't contaminate the groundwater. On the other side, we have to use chemical fertilizers. You know, here there is always advantages and disadvantages from every decision. But our results, definitely, they use they help the decision-making persons to make more objective decisions. Okay, then I will go to our second study. You know, when microplastics are reused in the environment, they don't stay as they are. Because in the environment we have lots of microorganisms, lots of other chemicals, and what we observe in the environment is that the behavior of the plastics changes dramatically. Some plastics that they are heavier than the water, when they enter in contact with the environment, suddenly they don't sink anymore and they float. Others that are less heavy than the water, we find them that they sink. Why? What happens in the environment? In the environment, we know and we show with our work that microorganisms, they colonize the surface of the plastics and they build a biofilm. And by building this biofilm, they alter the properties of the plastics. Another thing is that we also have chemical precipitation on top of these surfaces. And in this study, we investigated the formation of calcium carbonate deposits as well as the formation of biofilms on top of several different types of plastics. And then I will show you a brief overview of the results. You know, what we did was very simple experiments. We choose microplastics that are in great use in Germany, and then we incubated these microplastics for several months with different types of water, with tap water, with reservoir water, and river water. And then we took samples, you know, we incubated, we had a light, dark period, we had some gentle shaking, and a long time we took samples and we saw what is going on with these particles. And what was very interesting, from the first day we immediately saw changes, because some of the plastics that in the beginning they were floating, after some hours they sunk. And after some days they float again, because many processes were happening simultaneously on the surface of these polymers. And here, only to elucidate what type of analysis we did light microscopy. And what we see in light microscopy, we see that we have growth of bacteria on the surface of the polymers, but much more in suspension. This is normal. We use Raman spectroscopy to identify the chemical deposits. And then we did fluorescence microscopy with different dyes, different probes that target different bacteria. And what you see, for example, you see here, these particles, they are spheres. Inside, this is the particle. And all around the particles, you see fluorescence. And this fluorescence is due to the presence of microorganisms. It means with fluorescence microscopy, we detected the formation of biological films all around the particles. With light microscopy, we could see if the microorganisms, the bacteria, only grow on the surface or also in the medium. And with the Raman spectroscopy, we investigated the chemical deposits. And we did this for different kinds of polymers. We did for the PMMA, and we did for the PTFE. And what we can see is that the microbial growth depends on the type of plastic. Some plastics, they are more friendly for the bacteria, and the bacteria can grow much more, and other ones not so friendly. Maybe the carbon accessibility is more difficult, and bacteria cannot grow so well. Then, what is the message? The message is that the fate of microplastics in the environment may depend on the type of polymer, but also, more important, on the aquatic conditions that you have. It means you cannot predict the behavior of plastics into the environment based on the theoretical conditions. Because in the environment, the conditions, they change the polymer, and then they behave completely different. It means we need in situ studies to really predict what happens to our plastics. And now I'm going to the last example. And this example was for us a real nightmare. And I will explain why. In our wastewater treatment plants, we also have to treat the sludge, the so-called digester. It means the sludge comes to this digester and we have the production of biogas. But in this digester, to increase the amount of biogas that we produce, we can also put, for example, food residues. This is very, very common. Imagine in a market, they did not manage to sell all the food. This food is out of date. What can we do? We can put this food in the digester and produce more methane. What did people do? They did not take the food from the plastic, how can I say, all this food, as you see, it is inside, and you have a plastic foil or you have a plastic container, and instead of taking the food of the containers and putting the food in the digester, what they do? They just made a kind of trituration of the plastic and the food, and they put everything in the digester thinking, okay, this will disappear. But it did not disappear. And what happened? Some months afterwards, suddenly the river was full of plastics. And it was really a huge scandal. No one knew where this plastic coming in the river. And then the officials, they start tracking where the plastics were coming from. And they discovered that the plastics were coming from the wastewater treatment plant. And the wastewater treatment plant, they had a huge problem and they paid a huge fee. And they asked us to analyze the amount of microplastics that were circulating in this wastewater treatment plant and how can we take it out? Because they were not allowed to discharge into the river because they were completely polluting the river. And then we received this project. And here you see, this is tons of plastic that they had. And then I will show you a little bit of the results. This is the skin of the wastewater treatment plant. You see, I'm not going in much detail. I'm just going to tell you here. In the upper part, we have the so-called wastewater line. And the plastic were entering the river from this secondary clarifier. Before, they did not have this filter. And the effluent from the secondary clarifier was entering into the river and was bringing the plastics. I cannot imagine that the people in the wastewater treatment plant, they did not see the plastics, but they say that they did not see. And then, all these plastics, they were accumulating in the sludge. You understand? And in this digester, we digest the sludge, but the plastics, they do not disappear because they are not biodegradable. And what happens, we were circulating all the time the plastics in the wastewater treatment plant. And then we took samples. At several places at this wastewater treatment plant, we took samples to analyze the amount of plastics, what type of plastics, and to make a mass balance. And now I will show you some of the results. This is, to see these plastics, you don't need a microscope. You don't need a binocular. Even myself, that don't see very well, we can see with naked eyes. They are not micro, but they are macroplastics. It means the size is higher than 5 millimeters. How did we collect these plastics? We'll filter it, water or sludge, through this sieve. And like this, you see, we were able to collect the macroplastics. And then, these macroplastics, the composition was analyzed by infrared spectroscopy, and we analyzed the amount and the mass of the microplastics. But in this case, to separate them was easy because they were very big and we could use this big sieve. Then we weighed the plastics, we counted the number of particles, we studied the composition using the infrared spectroscopy. And here are only some examples. Look, we have the composition of the plastics in the dewatery sludge and into the wastewater that goes into the river. What you see, the diversity of the plastics is much higher into the sludge than into the water that goes into the sea, into the river. It means here you only have polyethylene and polypropylene because these are the lighter plastics. They float easily, they are difficult to retain, and then they go directly into the river. In the sludge, you have the plastics that are heavier. For example, you have the polystyrol, the PET, the PVC, the PE. These ones here low, they are heavier plastics and they stay into the sludge. And we quantify the percentages of both. We also quantify directly the plastics into digester, the different types, as you see, and it's not very different from the plastics in the water sludge. And then we needed a solution, because we could not continue polluting the river, but the wastewater treatment plant needs to continue working, because the wastewater is not something that you can store in the fridge to find a method, because you have many cubic meters every day. Then, here is only a picture of reality that you see the amount of plastics that we sieved from this wastewater treatment plant, and then we thought, how can we prevent the plastics to enter the river? Then we settled a filter. It means after the secondary clarifier, we put this filter to be able to retain the plastics. Okay? And here you see in the filter, the plastics stay there, and they are also captured because we put a buffer wall so that they cannot go into the river. It means, first, the company, the wastewater treatment plant, did not receive any more packaged food. This stopped immediately, but the plastics that were already in the wastewater treatment plant, we had to take them out of the sludge, and it is months. It's not a problem that we could solve from one day to the other. But preventing these plastics to enter the river is something that we could do immediately because we installed there a filter. Then I come to my last slide. What is the message for us, for all of us? First, reduce the use of primary microplastics. It means when you go to the supermarket to buy your gel douche, read the package. Read when you buy detergents for your home. Read the composition. If the composition has microplastics, don't buy it. Because if you buy it, you are actively contributing for the release of microplastics in the environment. There are other products that have a similar function and they don't use microplastics. That is up to you and me to reduce the amount of primary microplastics, just being careful in the selection of the products that we use every day. Second, reduce the use of disposable plastics. You know, sometimes we go to the supermarket and we buy this, we buy that, and then we come home with 5 plastic bags. Now in Germany we have a regulation that if you want a plastic bag, you have to pay it. Plastic bags are not anymore for free. And in the supermarkets, we cannot anymore have plastic bags. We have paper bags. It means we can reduce the plastics that have a very short life. Other plastics, sure, we cannot reduce. Many plastics that we are used in construction and this and that, we need to continue using them. But the ones that have a very short life, we can try to substitute. Fourth, we have to do more recycling, more separation and recycling. When we have our waste from our homes, if we put everything together, we cannot recycle. But if we have a recycling facility and we separate in the different kinds of waste, then it's easier to collect and easier to recycle. And then if for some of the plastics, we can think about of replace plastics by biopolymers. And this is also a topic of research between Professor Bauer and myself, that for some applications, instead of using plastics, we are going to use biopolymers. It means polymers that are produced by microorganisms and that they are biodegradable in the environment. And now this is my last slide. Thank you very much for your attention, for your patience, and if you have questions, please ask me.
We can take some questions.
Ma'am, good morning, ma'am. As you said, the water which contains microplastics goes into under soils and then goes into underground water. So, the water which contains microplastic, they affect the productivity and yield of crops in any positive or negative sense?
Now, this is a very important topic that is being studied, and there are not too many studies, but there are studies that show that these microplastics can go into the roots of the plants, and they can have a negative impact in the growth of the plant, because I spoke about microplastics, but there are also nanoplastics. And these nanoplastics, they are so tiny that the roots can capture them. And these studies are going on, especially the effect of nanoplastics in the growth of crops and other plants.
Ma'am, I have two questions. First is with the density, by using the density, we are going to separate the different microplastics, but definitely there are so many biofilms adhere on them. So, is there any, how can you remove that biofilm, and how you can separate that?
For the biofilm, you apply hydrogen peroxide.
Okay.
Now you make this first treatment,
Yes, ma'am.
iron peroxide, 70 degrees for a certain time. And then, what is the biofilm? It's organic matter.
Yes, ma'am. So
And
it will be
The
degraded.
biofilm are bacteria and are the exopolymers excreted from this bacteria. This is organic matter. And when you use hydrogen peroxide, it is an oxidation agent. It destroys the biofilm, and then you have the clean plastics.
Okay, ma'am. And my second question is that there is any extraction method of that nanoplastic and microplastic from the ocean also? Means we are working in that area or not? Means we are extracting from the river. So there was a huge pollution of plastic in the ocean also.
Yes.
So is there any method for extracting that polymer from ocean?
Yes, I know that. I know that there are companies that they develop a technology to catch the microplastics from the seawater. But you also have to think one thing is that we have microplastic in the seawater, but we have other microplastics in the sediments. It means we are starting cleaning the microplastics that are in the water column. That is starting now.
You said that for the filtration of microplastics,
You have to choose the filter paper depending on the size of your microplastics. Imagine, if you want to recover microplastics that are in the order of 1 milliliter, 5 milliliters, you have to use a filter that has a filter port smaller. But always choose the adequate filter, because if you choose, you say, okay, then I'm going to use a filter that has a very, very small pore diameter. Only if you need it, because these filters, they clog very easily. Then what I suggest is to make like a sequencing filtration using filters with different pore sizes, and you start with a filter that has a bigger pore size that collects the bigger particles, the smaller particles they go through, and then you have a second filter with smaller diameter and a third filter. Because if you go directly to the filter that has 0.2 micron, and you go directly with your initial solution, after 2 minutes the filter is clogged and nothing works. Yes?
so we frequently use plastic bottles for storing and carrying water. So do these bottles release microplastics into the water or anything else?
it depends on the time your water is a plastic bottle. Because when you buy the water, you drink it in the day or in the week. But when you buy a plastic bottle, you don't know how long this plastic bottle was stored somewhere. You know, it can be stored from 1 month to 6 months. And with this time, the plastic is slowly degrading. I cannot say that you will have a huge amount of microplastics because this depends on the type of plastic of your bottle. It depends on the additives that they use to produce the plastic bottle. You know, one thing is the plastic itself, but then to produce a certain product, you need certain characteristics. And many times you need to change the characteristics of the polymer by adding additives, so that you have the properties that you need to produce a plastic bottle. It means if your bottle will start degrading depends on many factors. It depends on the type of polymer, it depends on the additives, it depends on the storing conditions, and it depends on the chemistry of the water.
What happens if we consume microplastics?
No one knows very well. You understand? No one knows where are these plastics going to accumulate, in which organs they can accumulate. Can they go to the brain? This is now that this, especially the nanoplastics, is a huge topic, and they started the accumulation in marine organisms, but always the question comes, what happens to us? It means in our life, we drink many liters of water. Imagine if you calculate that every day we drink 1 to 2 liters of water, you can, and if you say, okay, in 1 liter of water I have 10 particles of microplastic or nanoplastic, you can calculate how many you could accumulate per year. And then, do we excrete them with the urine, or where they accumulate? And these studies are going on, because these studies are not so, how can I say, when you have an organism that multiplies very fast, you can do this, you can expose them to certain doses of the microplastics and see the effect. But on us, it's not very easy to assess where they are accumulated unless you are looking for, and these studies are going on.
I have a question for you. Like you showed here the formation of biofilm over the surface of plastic. So possibly those bacteria may be degrading those plastics. So I remember reading a paper where they have identified bacteria that degrade the plastics, but their efficiency is very low. So I'm quite interested in knowing that. Are you working in this field of increasing the efficiency of bacteria to degrade the plastic? Because I think this is a very good alternative where we can use microorganisms to degrade plastic. So,
maybe I will tell you, I forgot to include in the presentation. I have been working in a project where we produced biopolymers, in this case PHAs, and these biopolymers we have biodegradability studies in situ. It means these polymers, they were put in the Mediterranean Sea. They were put on the beach, on the sediments, and they stayed there for a certain time, and then we collected them and we sequenced the biofilm that is on top of the plastics. And now we are identifying which microorganisms are in this biofilm. But you know, your idea, what you are proposing, makes a lot of sense when we are working in a biotechnological application. It means we have the plastics, we put the microorganisms, and they are degraded. But if you are in the big ocean, you cannot change the conditions. You cannot change the pH. You cannot change the temperature. The organisms that are there, they will continue working slowly. You can use microorganisms if you can catch if you can recover your microplastics, and then you can treat them. But for in situ treatment, you have to live with the conditions that you have.
Ma'am, I have a question. So in one of your experiments, you used tap water, river water, and you put in different kinds of plastic to observe what the effects were. So microplastics might already be present in the tap water and river water. So does it hamper the results?
Sorry?
In one of your experiments, you used tap water and river water, and you put in different kinds of plastics to see the effects of degradation. So, microplastics might already be present in those water samples.
Exactly.
So,
Imagine now you are a scientist. Your question is very relevant. You want to exclude the effect of the microplastic that might be present in the water. Which kind of control would you add to your experiment?
we could use filtered river water.
Very well. It means at the beginning we filter river water, tap water, and dam water, and we observe what do we have there to characterize our water. And then we took this water and we add these plastics. It means we have like a blend assay, not to have false positives. It means in the planning of your experiment, you always have to think. And this is what we did.
Thank you, ma'am.
Okay, I see no more questions. I think you are tired and we need to go for lunch.
Thank you, Dr. Regina Nogueira, ma'am, for your wonderful talk. So now I would like to request Dr. Kiran Bala, ma'am, to present the token of appreciation to Professor